Welcome back. We are now ready to move to lecture 11 and finally talk about the elephant in the room, which is energy. So today in this screencast, we are going to talk about energy. We are going to jump right into the first law of thermodynamics. And the first law of thermodynamics uh, clarifies a little bit what we mean by energy, but also help in understanding how we can transform one type of energy into another one. Well, not so much how, but the fact that we can do it, and also how we can relate heat and work. Along the way, we are going to focus on one very important concept that's going to be crucial for the rest of this course. And this concept will uh, be about the difference between function of state and uh, variable which are not function of state. So we are going to decide that, and in fact, a lot of difficulties of thermodynamics come from mixing those. So we are going to discuss this in detail in this screencast. So let's try to go back to something we did in lecture 4, and we discussed about thermal equilibrium. And so the thermal equilibrium corresponds always to a given system. So that's yet another misconception sometimes of thermodynamics. We have to make sure that we know what system we are considering, so that we know what is the input, what is the output. And if we talk about an isolation of a system, of course, we know that that system cannot have input outputs, for example, in terms of heat for a thermally isolated system. So the point remains that we have to think about the system as being a well-defined part of the universe, or could actually be the universe. In this case, it would be a closed system, depending on how we define it. Okay. So of course, there's a system and there's the surroundings. So this is something that we have to think about. And then we know that we will have a system in thermal equilibrium when its macroscopic observable F do not change anymore. So typical thermal equilibrium observable are pressure. It is pressure and temperature. And just let me remind you schematics I showed you in lecture 4. When we start from two subsystems at different temperature, and when we let heat flow from one to the other, we end up with a thermal equilibrium where the temperature of the final system is well defined. In fact, the pressure was well defined as well. We didn't discuss that too much. Okay, so this is called the thermal equilibrium, which means there is a set of variables that describe that state. Okay, and so this is what we are going to discuss now. We're going to discuss about those variable of state that basically describe the state well. Okay, um, so we are talking here about, of course, a equilibrium state for the macroscopic observables. Another thing that I'd like to mention here, imagine that you have a container of molecules of gas, just the same way we did in the past 3 lectures in the kinetic theory of gases. Um, if we consider that system, of course, it has at equilibrium, it is a well-defined pressure, it's a well-defined temperature, well-defined volume as well. Yet, if you were looking at the microstate, at every single individual particle or every single individual molecules of gas, they are still moving about quite a bit. Yet, this is an equilibrium because we define the thermal equilibrium as that equilibrium where the macroscopic observables have ceased to change. We are not talking about the microscopic observables, such as the velocity vector of a specific gas molecule. So this is again something that's important to differentiate between microscopic event and macroscopic observables. That means that we need a number of functions of state, and those functions of state will define the the state itself, so the equilibrium state. Okay, so um, this would be, for example, temperature, pressure, volume, total energy. And what is really important to understand, that this is going to be crucial for the rest of this lecture, but also for the following of this course, is that those properties do not change they do not depend on how we got there. The point is that if somebody gives you a system that's a certain temperature, pressure, and volume, uh, those properties do not depend how we got there. Okay, so this is the reason why they're called functions of state, though they're only depending on this particular state. Okay, so that's very important. Uh, we sometimes call those function of state also sometimes variables of state. It turns out that function of state is a bit more general because they are going to describe even combination of variables of state. And this is for the definition of what a function of state is. It's a quantity, a physical quantity, something that can be observed that has well-defined value for each equilibrium state of the system. Okay, so if you have an equilibrium state of the system, it has well-defined values such as, again, I said that again before, temperature, volume, or pressure, so or energy. So of course, sometimes it's easier to define things by saying what they are not. So example of quantities are not functions of state. The position of a specific particle, I described this to you a few seconds ago. The total work done on a system and the total heat put into the system. So these two topics are the most difficult topics to really master for students who have never done this before. The point is the work done on the system and the heat that's transferred into the systems are not functions of state. We shall see in a second the sum of them is a function of correspond to a function of state, but each individual component do not. So an example for this is like, for example, imagine that you have warmed your hands. So it's an example that's modified from, that's borrowed from the book, again, from the Blundell and Blundell book that we are following in this screencast. So imagine that you have warmed your hands, okay? You could have warmed your hands in a number of ways. You could have rubbed them against each other. You could have put them on a heater. You could have done anything else, like just to get them warm in the hot water, okay? The amount of heat that got into there is different in each case. And yet the temperature, so the variable of state for your warm hands is well defined, and yet the amount of heat, the way the temperature was reached, can be done different ways. Okay, so you can think about an example I discussed. There is some work involved in some of them and less work in others. Okay, so we are going to of course clarify all this in a second. So now, as always in physics, the beauty of the way we do physics, at least modern physics, that's no longer an empirical science, just an empirical science, is that we are able to translate those concepts into very firm mathematical ground. And so that's what we are going to do. So remember, what's a function of state? A function of state is those variables or those functions that do not depend on the path it's taken to get there. Okay, so in contrast, if we have a variable that is not a function of state, that means it depends on how you got to a point, to a thermal equilibrium. Okay, so these are the definition. So how can we translate this mathematically? Well, let's suppose that I have a number of parameters, and let's suppose that we have a function of state f of those parameters. So of course we have different type of combinations. It could even be the parameters themselves, right? Parameters could be temperature, volume, energy. And the idea is to understand, to understand the changes in this function of state. So let's try to suppose that we have a system that go to the initial state to a final state. So label I and F with the list of parameters placed into vectors. And of course, we can calculate the change in the function simply by the value of the function at the final state minus the value of the function of state at the initial state. Mathematically, we know that if we can write a function like this, that just depends on the boundaries, we can calculate an integral where we have an exact differential inside, right? This is almost the definition of differential, of exact differential. So that means that f can be written, we can write f this way, where we have a perfect differential df. So that's a very interesting example here, because that means that if we can write a certain function of state so that the integral is just the differential of the function, then we have a function of state that's almost synonymous. So the mathematical definition of a function of state would be one that can be written, for which the integral can be written the way it's written there on this slide. So that's crucial. So this exact differential is synonymous to a function of state. And that way we know that the variation in the value of the function of state only depends on the final and initial state. In other words, it do not depend how we got from initial to final. Okay. So on the other hand, if the quantity we're talking about is not an exact differential, that it's not a function of state. So why do we make such a big deal about this? Well, we make a big deal because if we are dealing with a quantity that is not a function of state, we have to worry about the path that the system is taking to get from one state to the other. So that's actually crucial, because this is the importance of thermodynamics. Now, on the other hand, if we are lucky enough to be working with a function of state, in that case, we only have to worry about the initial and final state. The problem is, in thermodynamics, we are dealing with both. So we have to be extremely careful. Okay. So I'd like to show you additional two examples here, just to make the point clear. So suppose that we have a function that can be written just two parameters, and it's x times y. So the derivative of this function, the differential, the df will be dxy, so it can be written y dx plus x dy using the chain rule. And that means that I can actually calculate the integral of df, right? So if we want to look at, for example, those three plots that are below, we are just going to look at the first two on the left. And the first point is at 0, 0, and the second point is at 1, 1. And we're interested to know what's the variation in that function going from 0, 0 to 1, 1 using the different paths that are shown at the two left figures. So the first figure will simply obtained by the calculation I show there. And we see the variation to go from one to the other will be equal to 1. On the other hand, if we want to look at the other function, we also see that we can do the same thing. We can actually calculate this as going from 0, 1. I mean, sorry, from 0, 0 to 1, 0, and then from 1, 0 to 1, 1, and we obtain the same result. We obtain 1. So that means in that case, we have an exact differential. So the answer is independent of the exact path taken. So I invite you, if you have any problem, I invite you to stop the screencast here and to do it yourself, to convince yourself. Of course, again, it's easy to show an example of an exact differential. So it's essentially a function that cannot be written in just like we did before as df, for example. The example would be this one. And actually, I'm going to go back to this notation in a second. This is not dust on your screen. There is actually a bar, an horizontal bar in the D for dg there. So we do this so that it's a small change in g, but it's not a differential. Okay, so it's, in other words, if I integrate dg with a bar in the d, I cannot just say this is equal to g evaluated at the initial and final state. It's a very handy notation to show that when you have a d bar, that means that it's not an exact differential. Okay, it's just the bar, just the d bar just shows that we have small changes in g. Okay, and those small changes in g will depend on the path that's taken. So let's suppose we take y dx, and then we are interested in calculating also the variation just along the same path as before. So you have the first path that we considered before, and you find, of course, that if you do that, you're going to find that you find a 1/2. I mean, it's just a matter of replacing. In this case, the way we did it was replace y by x, since the path is the bisector x equal y. And then, if of course, if we do it the other way, we can do it this way as well, where we initially just go from 0, 0 to 1, 0, then to 1, 0 to 1, 1. And when we do that, we find that this integral is actually 0, which is not surprising. I mean, basically, this is the surface area under the curve. So we see that in this case, the total change depends on the path, and this is very important. So let's go back to the function of state. They can be extensive, as we've seen before, they depend on the system size. They can be intensive, they do not depend on the system size. And the idea of thermodynamics is to find equation of states that can actually connect those different variables, okay, so that we know the dependence between, let's say, temperature, pressure, and volume. That's what we've seen for the ideal gas. But we can actually calculate different type of function of states, and this is exactly what we are trying to do in thermodynamics. In fact, in thermodynamics, we will see that we are going to introduce a number of energy-related function of states. We are going to spend a full screencast on this later. But what's important to remember is that we can have function of state that are either extensive or intensive. So that's not, it doesn't disqualify a variable from being an exact differential, even if it's intensive or extensive. Okay. And the second thing is that, and I'd like to really insist on this, what we will really be interested in is variations. So a course of thermodynamics is usually not very attractive to students because we see a lot of partial derivatives. And partial derivatives somehow make the reading of the equation pretty tedious sometimes. But there is nothing really complicated in this. It's just, again, this is one other example of notations scaring students away. There's no reason for that. It's just, if we take everything step by step, there shouldn't be anything really complicated. Okay, so that was a long parenthesis to talk about function of states. Remember that we were talking about energy at the beginning of the screencast, but I think we have all we need now to understand energy. I mean, to start to understand energy. Okay, and let's not just let's just end the dance here and just go back right at the first law of thermodynamics. And in fact, the first law of thermodynamics, as many laws in physics, were developed over the years, so there is a history behind them, and so there are different formulations. This is particularly true in thermodynamics, a number of different formulations of the same law. The initial one coming from Joule was that there is an equivalence between heat and energy. So this is something that people take for granted now, but it's not always been the case. Why different forms of energy different form of energy can be possible, like work, heat, and energy. And that definition was actually was clarified and improved, I should say, by Mayer and Helmholtz, who just said that energy is conserved, okay, and heat and work are both forms of energy. And there are, in fact, both forms of energy that can be exchanged between each other with some restrictions that will be dictated by the second law of thermodynamics. So this is really important here. So fundamentally, heat and work are both forms of energy, and total energy is conserved. So this is an important thing. So when we talk about total energy of a system, the typical definition we use for this is we don't say total energy of the system necessarily, we are talking about internal energy. So the internal energy is really the variable that we are interested in. And so that's the total energy basically that's conserved. So it's a variable of state, and this is the internal energy U is the sum of all the different forms of energy basically. Okay, so that's one way. It's a container that contains all the forms of energy, and that particular one is a function of state. It has a well-defined value for an equilibrium state of the system. That's the idea. Okay, so that's good. Uh, I mean, you can think about different example of how you go from an initial state to the final state. It doesn't matter how you got there, the total energy is the same. I like to think about um, a kid who goes down a slide on a playground. If the kid start at zero velocity on the top of the slide and gets to the bottom of the slide, and there are different slides in those playgrounds. There are different types. Some are longer, some have more twists and so on. Doesn't matter. Doesn't matter which slide the kid took. The kid took. Uh, the energy at the top and the energy at the bottom are the same. So this is an example of a case where the final and initial state are well defined. They are equilibrium states, and they have a total energy which is um, which is in fact well defined. It means that the energy is a function of state. Of course, what happens in between, there is some heat, there is some speed, there is all different kind of energy that's transferred. But all those things are not function of state, but the total energy is. So now what's important to know is the heat and work are not function of state. I already mentioned with the way you rub your hands, but this idea of the slide, the kids on the slides is also another example of this. Um, the problem with this is that work and heat, because they are not function of state, they will depend on how things have been done. So again, this is a case where students get in trouble sometimes because they forget that heat and work, so those changes depend on the path it's taken. Okay, so the the fact that they are not functional state, just like it's written in that last line, simply means that even though we can consider that the total energy is include both the transfer of heat, but also work done or work done on, um, we don't know what contributed to the total energy. We just know what the total energy is. Okay. I hope I made this point clear. So mathematically, it simply means that changes in internal energy will be related to changes to the transfer of heat to the system and then work done on the system. So this is a change in internal energy. Now, this is another point of, of confusion for students. I'm really sorry that I'm bringing so many points of confusion for students in this screencast, but maybe you can watch it a couple of times to make sure that you are comfortable with everything I'm saying. But there is an issue with, it's not an issue, but there's a convention about the signs that we use for the different components. So the way we decide these things is delta Q will be positive if heat is supplied to the system. Okay, so if heat is supplied to the system, the delta Q is positive. Likewise, if work is done on the system, then the delta W, so delta W is for work, will also be positive. So somehow students are confused about the sign because most students understand the system. For example, if you take just a person as a system, understand that heat supplied to the system is positive. They get that, but work done on the system is usually think that is the work done by the system that's positive. But no, it's not. So essentially, you have to think about this, what we call the selfish, what we call sometimes the selfish convention. That's what's positive. It's what comes to you. Okay, so if heat is transferred to you, it's positive. If work is done on you, it's positive. Okay, so this is something that you don't want to get wrong, because if you get the signs wrong, all the thermodynamics is falls apart. So just let me remind you. So if you always have to think about the problem as a system as a whole. So the system, the change in internal energy of the system will be positive if work is done on the system and if heat is provided to the system as well. Good. Now we can consider a number of different cases. One case that we will see a lot is thermally isolated system. So thermally isolated system means that the system cannot exchange heat with its surrounding, okay? So the system cannot exchange heat with its surrounding. That means that when we wrote delta U is equal to delta Q plus delta W, we can drop the delta Q. So in that case, for a thermally isolated system, the only changes in internal energy can be brought about by changes of the work done on the system or done by the system if it's a negative number. Okay. Now let's go back to this general equation that delta U is equal to delta Q plus delta W, which is essentially a mathematical expression of the first law of thermodynamics, that delta Q and delta W are two forms of energies and can therefore be exchanged. Okay, we'll discuss this more in detail. Now, in physics, and mathematicians are much more careful than this, but physicists usually feel totally free to replace a delta, which is a finite difference, to a d, to a differential difference, right? So this is very typical to do it. Well, we have to be careful here because remember what I mentioned a minute ago, that even though the internal energy is a function of state, therefore that there is such a thing as a du, heat and work are not function of state, right? Because we can have systems that are the same system in thermal equilibrium, which would have gotten there by different means, so different delta Q and different delta W. So therefore, that means that the changes in Q and change in W are path dependent. And if it's path dependent, by definition, it's not functions of state. So we cannot write dQ and dW. So the convention that's used in the Blundell and Blunder book is, in my opinion, excellent because it removes all that confusion by writing a D bar. The D bar means that you cannot just put that D, it's not an exact differential mathematically. That means that you cannot simply put this into an integral and evaluate the value of the function at the boundary of the integral. So that's very good to do. Okay, so we can ask ourselves, how can work be done, or how can we do work? And the typical thing for work that we use in thermodynamics, even though there are a number of them, but we are going to focus on one in particular, is basically work is a displacement of a force, right? So in principle, we know it's force, it's a dot product between the force vector and the displacement vector. So in one dimension, this is the force, for example, along x times dx. Okay. So if the system here is a wire, we know that the work done on the wire, okay, is f dx. Okay, good. Now, if one case that we will do again is the ideal gas or the gas in general. So we can think about work. So I'm going to spend a second on this because it's going to clarify a little bit what we mean by positive and negative work. So if we have the system, if my system is defined as the gas container, okay? So if somehow there is a pressure that pushes on the piston, and this means that the volume changes, is actually a negative change in volume, right? So dV is negative because the volume is lower. So clearly pushing on the gas is work done on the system, right? It's really pushing, making the gas basically decreasing the volume, right? So that means that dV negative, so that means it's work done on the system, so it's a positive work. Clearly, positive work, it's done on the system by convention. So clearly the work is minus PdV, right? Since dV is negative and P is positive. So minus PdV will be a positive number, and which is exactly what I want for work done on the system, okay? So just to be clear. And in this case, what we can actually see is that if if this work, this PDV minus PDV, sorry, is done in a reversible manner, we can work something like this. The reason why I say reversible manner is because there are other ways that if you go fast, for example, you can create shock waves, you can create all sorts of things, or if the system, if you have different type of material in there, uh, this is not always the case. But for our purpose, we are going to see that the work is going to be minus PDV. One thing I'd like to attract your attention on is that, interestingly enough, P and V are both functions of state, okay? But minus PDV is not, okay? The work is not a function of state, even though it's made up of functions of state. That's something that's interesting to note. Now let's move to heat capacity. Heat capacity, this is one of the first variable that we've met in this course. And heat capacity is about the amount of heat that's transferred to a system to increase its temperature. Well, in fact, when we were increasing the temperature, what we were doing is we were changing the internal energy, okay? So it's interesting to go back and look at this problem from the lens of what we learned so far. And you will be surprised that in just a few lectures, we've already learned quite a bit, and we can already make important conclusions. So let's do it. So we know that the total energy is going to depend on the temperature and the volume, right? So you can also say, well, what about pressure? Well, we know that there is a relationship between temperature, volume, and pressure, so we don't have to worry too much about that. So when a function has multiple variables, we can use differential calculus and partial derivatives to say the total variation in the function u can be calculated by change variation in the function for one parameter, t, times variation in t, plus a variation of that function u as a function of volume times variation in that volume. So now what is important here is the subscript v and t that we see in this equation, simply because each differentials, partial differentials, each of them is calculated but while keeping the other parameter constant, right? So this is what we learn in calculus. This is where some students already give up. There is nothing to give up about. This is as straightforward as it gets. You just have to be patient and be careful about your indices and so on. There's nothing complicated. Okay, this is something we already know, but we also know this, right? So this equation, I just rearranged the du equal dq minus pdv that we had on the previous slide. So that's an expression for the variation in heat. And of course, I can write variation for heat as also variation with, I mean, I cannot use the rules of differential equations of finite difference and so of differential calculus. Sorry. Here, since the d bar q is not an exact differential, so I have to be careful about this. Instead, I can substitute the value of du and from the middle of the slide, and I can actually substitute it directly in the definition of dq, right? The first law of thermodynamics. So by doing this, I obtain the equation that's on the right hand side of the blue arrow, and that's very good because we are getting somewhere. Now I can also calculate the variation of Q with function of temperature. Basically, if you want to say it quickly, you are essentially divided by dt everywhere on the left and the right, and you get this equation. That's quite nice. It's a variation, it's a change in heat as a function of temperature. So that allows me to go back to the heat capacity. Remember, heat capacity was the amount of heat that I have to bring to a system to change its temperature to the temperature from 1 Kelvin. And that's very interesting because remember that we had two types of heat capacity, one at constant volume and one at constant pressure. And we are going to be able to calculate this now. And this is what we get here. In fact, we can get the CV, which is the change of heat as constant temperature, at a constant volume, sorry. And you see that at constant volume, the right-hand side of the equation, the bottom left of the slide, disappears because you have a dV over dt. So if V is constant, of course, dV over dt is 0. And that allows me to calculate CV. And of course, in this case, CV will be the variation of Q over delta T by definition, which in this case turns out to be the variation of U with respect to T at constant volume, right? It's what the bottom equation on the left says. And we can do the same thing for pressure. And when we do this for pressure, we essentially calculate the variation of the heat that will lead to a change in temperature of 1 Kelvin, and we can do the same thing. And you will see that the way it's calculated from the equation we have on the bottom left is simply by imposing the pressure to be constant in all those equations. So the differential equation that were already calculated, the the derivative that were already calculated, are numbers at this point, right? So we do not have to change pressure to impose the constant pressure or anything like this. That's very good because now we have mathematical definition of CV and CP, so the heat capacity at constant volume and constant pressure, as a function of other functions of state like U, T, V, and P, which is excellent thing that we've done. So of course we can calculate the difference between CP and CV and obtain this very simple this fairly simple equation, and we can define specific heat capacities. Again, this is the heat capacity divided by unit of mass. This is usually what it's done. Okay, let's go back to the heat capacity of an ideal monoatomic gas. Why do we do that? Well, because we can use that equation PV equal nRT, and we can also use solution all sort of properties that we got from the previous lectures. In particular, if you go back in the 2 lectures ago, I would say, not the last lecture on collision, but the lecture on pressure, we found that the internal energy for an ideal gas is simply 3/2 times RT for a mole. So the internal energy only depends on the temperature. Okay, this is something that we found. It was a very important result we discussed. We actually discussed it was 3/2 kBT, but since we are per mole, we divide by the Avogadro number, and so we are all good with this. Okay, so what's nice is that we have a very simple description of the total energy, of the internal energy, and so the derivative that we have to calculate will be nice. And in fact, if we want to calculate the derivative du over dv at constant temperature, we'll see that we have 0, right? So you can say, well, temperature depends on volume. Yes, sure, but we are keeping temperature constant, so it's just a number when we do the derivative. So that's nice, and so we find this is equal to 0. So the first differences there are 0. On top of that, for a mole of gas, of course, we still have the ideal gas law, PV equal RT for mole. So that means that I can calculate the derivative dV over dt, and this is simply R over P, where P is the pressure. Okay. Now I can put all this back together in the equation, and what I found is that CV is actually 3/2 R, and CP is 5/2 R. So that's something that's quite stunning, because for an ideal gas, CV and CP are very simple formula that should be constant. It doesn't matter which gas we have. And also the difference between them is a constant. It's actually R. So the difference between CP and CV is R. And as we discussed before, CP is always higher than CV, simply because we need to provide more heat in a system on which we also do some work. But if the volume is constant, there will be no work done, so we need less heat to increase the temperature by the same amount. So that's the reason why Cp is always larger than Cv. In fact, we know what's the difference is. It's R. Okay, so that's very good. One thing that we like to usually define, because those results are only true for ideal gas, so sometimes we want to know how far from an ideal gas we are. So we can calculate the difference between Cp and Cv if we want, but we can also calculate the ratio between them. So the ratio, and there's a name for that, it's called the adiabatic index, gamma, and the adiabatic index gamma is Cp over Cv. So basically, gamma is going to be equal to 5/3 for a perfect gas. So the thing is that Cp and Cv can be measured experimentally, and we can see how far we are from the perfect gas. And in fact, I just went to get some data from Wikipedia, and we can use those data from Wikipedia to compare how far we are from perfect gas. So this is some result I obtained from the Wikipedia page. And I only selected those systems that are in the gas phase. So just so you understand a little bit this table, we are talking about isobaric, which is constant pressure, and isochore, which is constant volume. We'll discuss those things a little bit more in detail later in this course. And I added the last column, Cp over Cv, which is, of course, the adiabatic index. So what I like you to focus on the last two columns. The first, and this is the first one is Cv, and we know Cv should be 1.5 times R for an ideal gas, and we see that the data there pretty close to 1.5 R. It is the right order of magnitude, even though the model is pretty crude if you remember how we got it. In fact, we have a very good description for argon and neon of 1.5. It's not surprising because argon and neon are very close to an ideal gas. They are monoatomic molecule, and they essentially do not interact with one another because they are closed shells. So there's very little chemistry between the molecules. So what's also interesting is to calculate Cp over Cv. That's on the last column, and again, we would expect 1.667, right? 1.66667 as for an ideal gas. And we see that again, those values are all, I mean, they're not exact, but you would not expect that. But they are pretty good, actually, even for air, which is the gas that we deal with the most of the time. So that means that the ideal gas law is actually not bad at all to use those things. So that's good. Let's look at one more important result that we can obtain from this equation that we studied. So we did this equation, and that allowed us to write this equation back. So 2 slides ago, you want to check that. And do not rely on your memory. Instead, think about the fundamental aspect of this and put all this together. But the point is, du equals Cv dt plus du dv at constant temperature times dv. This is true in general. However, for the ideal gas, U only depends on the temperature, and that means the second term is 0. So for an ideal gas, we have du equals Cv dt. This is a result that's actually used a lot. It is used a great deal, but it's truly only correct for an ideal gas. So this very simple form that U is equal to 3/2 RT for a mole of ideal gas is only true for an ideal gas. But this is a very compact way to say that for an ideal gas that the internal energy can be calculated as Cv times dt. We can even go further if we want to, and see what happens if Cv does not depend on temperature. Then we can integrate left and right, and that means that we can use this equation U equals Cvt, and we can calculate the internal energy per unit volume and per unit mass for an ideal gas. So here we're just going to apply those equations. So here, of course, the most important thing, as always, is that U equals Cvt, which I just reminded you how we got it, and then the equation for an ideal gas PV equal nkBT. Okay, N being the number of molecule. So we can define the density of the matter as Nm over V, N, large N, the number of molecule, M, the mass of each molecule, and V, the volume. So of course that gives me a density, right? And so we can substitute this into the ideal gas equation, and to obtain P over rho equal KBT over M. We also know, and this is something that you can calculate fairly easily, that CV equal R over gamma minus 1. I mean, just substitute gamma from the definition we had to the adiabatic index, and then we get, of course, CV equal R over gamma minus 1. And that means that we can calculate the internal energy just by substitution of what CV is and what we obtained before. And finally, we find that the internal energy per unit mass can simply be calculated as being a pressure divided by some constant, a density, and then gamma minus 1. Okay. So in other words, the internal energy is going to be related to the pressure. This is not surprising at all. We've already seen a result that's very similar to this for the ideal gas when we studied the pressure of an ideal gas, where we had the energy density was actually related to the pressure. And in fact, if you remember that gamma is equal to 5/3, 5/3 minus 1 is 2/3. So in fact, we find that the internal energy was 3p over 2. So that all makes a lot of sense. So it's just a way to manipulate the different variables, and you see how we are building all this thermodynamics by adding an ingredient each time. So it was a very well-packed lecture. Take your time to review everything because it's a very important concept that we need to study. What we studied is a function of state, and we discussed that they had exact differentials. This is very important. We identified those that would not have a differential, an exact differential, as so they are not function of state like the work or heat. And in that case, we use infinitesimally small changes by a d bar. Okay, we find that the change in infinitesimally small changes in work, again, is not an exact differential, but can be written n minus pdv for a reversible change. So one where we don't have all the difficulties related to the non-reversibility. And all this allowed us to calculate CV and CP, and we have basically manipulated the differences coming from differential equations from just the derivatives, so the partial derivatives. Important result we found is that Cp minus Cv is a constant for an ideal gas. And we also introduced the adiabatic index gamma is equal to Cp divided by Cv. So this concludes this lecture 11. There are a lot of important concepts here, and please take your time to review this. Open the book at chapter 11, and make sure that you also look at the exercises.